Welcome back to Built to Last. I'm Ted Bennett, and today we're in St. Louis, Missouri to investigate why the bridge named after James Buchanan Eads that was constructed in 1874 was built to last.
Infrastructure is built for many different reasons. A lot of infrastructure solves today's challenges, some solves tomorrow's, and a few projects revolutionize an industry while connecting a budding nation. That's what happened in St. Louis in 1874 when the St. Louis Bridge opened. The St. Louis Bridge connected St. Louis, Missouri with Illinois town, today known as East St. Louis, bridging the mighty Mississippi River. But not just bridging the river with some cheaply built truss. No, not at all. The bridge we know today, 151 years later, started with a vision, perhaps a crusade. James Buchanan Eads Bridge connected East and West in America and at the same time changed bridge engineering forever. This is the story of Eads Bridge, a story of true built-to-last infrastructure. But before we get to the bridge, let me introduce you to one of the most unique individuals you'll ever come across, Captain James Buchanan Eads, cousin of President James Buchanan, a boy who grew up reading engineering books and living on the riverfront. Eads got his start in business salvaging steamboat wrecks in the Mississippi River, designing one of the first ever diving bells, and later his own barges for lifting these wrecks. Eads was always inventing and seeing a business side, even negotiating exclusive contracts with insurance companies to recover lost cargo on the Mississippi. Then, during the Civil War, Eads spun his somewhat limited boat building experience into contracts to build ironclads, even patenting a gun carriage. Eads was never one to let inexperience slow him down, always finding the right experts to support his plans. When it came to ironclads, Eads discovered a new material, light and strong, steel. Eads was a creative visionary who hated the orthodox. This alienated many engineers because he cast aside conventional and what he called slowly innovative engineering. After the Civil War ended, Eads began looking at the need for a bridge in St. Louis. His fixation on steel as a structural member ever growing. Steel, largely untried in structural use at the time, was light and strong in tension, but more importantly, strong in compression. Eads envisioned a grand three-arched bridge with two stone piers set in the Mississippi, arches in compression, a roadway on top and a double-deck railroad on the bottom, arches using steel. Bridge experts smirked each design, saying it would never stand. Ever confident, Eads pressed on, rounded up the financing, and started on the construction of the abutments and the piers. The bridge experts proposed simple and efficient trusses similar to those that had already been constructed upstream on the Mississippi. Eads ridiculed those designs as uncreative and cheap, with no architectural beauty whatsoever. Eads even went so far as to have Congress modify the bridge's charter to rule out the construction of a bridge with spans shorter than his proposed St. Louis Bridge, always looking for an edge to keep the competition out. Even the pier construction was a major challenge from go. The Mississippi River runs at over 10 feet per second, and bedrock is located some 100 feet below the surface of the water. Eads knew the currents that ran on the bottom of the river from his days in the boat salvage diving bell. The construction of piers in the Mississippi at St. Louis would require a completely different method. Eads had made several trips to Europe to recuperate from a lifelong breathing problem and to gain connections in the steel industry. In addition to gaining insight into the Bessemer process for steelmaking, Eads visited the Pont-à-l'État bridge construction in France. At Pont-à-l'État, piers were being constructed using an underwater method called pneumatic caisson, which involves an open box or caisson being sunk into the riverbed while towers are being simultaneously constructed on top of the caisson. Once the caisson reaches bedrock, it is then filled with concrete. So, without settling the design of the bridge's steel superstructure, in 1867, Eads convinced investors to fund the construction of the piers and abutments, and construction started immediately. The caissons extended down, and the workers, called submarines, began doubling over in pain as they exited the pressurized caisson. They had contracted the bends. It was unknown what caused these crippling and sometimes fatal convulsions. To examine the causes, Eads hired a doctor, but in his trademark phrase, drive on, Eads drove on. The caisson construction extended to depths beyond where any previous caisson construction had gone. Eads refused to be limited to things that had been done before. As the project threw challenges at Eads, he just pivoted and designed something new. The doctor eventually determined that reducing the workers' exposure to compressed air and slowing their return to normal atmosphere helped. Eads looked upon the problem as an opportunity for a solution. Nothing would stand in Eads' way. Even the facts of the project's funding or cost, often presenting figures, sometimes false, that supported the goal of keeping the project moving. Nor was Eads waiting for steel design to catch up. The Great Bridge was now underway. In a typical Gilded Age cronyism deal, Eads worked out agreements with Andrew Carnegie and his associates Tom Scott and J. Edgar Thompson, who collectively owned the Pennsylvania Railroad and Keystone Bridge Company for the provision of unproven steel materials. Now, the Pennsylvania Railroad and Keystone Bridge both stood to benefit from a completed bridge at St. Louis. And Carnegie tried time and time again to deter Eads from using steel. It's too hard to make in sufficient quantities, too hard to get the quality needed. Eads was hearing none of it. To address the steel fabrication, Eads hired mathematician William Chauvenet to work the stresses in the arches. Eads then fired Carnegie's steel fabricator and hired William Sellers, the leading steel expert. With quantified stresses, the engineers understood the strength needed from each member. Then, each component was tested to pass or fail the steel components. In the end, only the arches ended up being constructed of steel, with the remaining portion of the bridge being constructed using the more common iron. The evaluation and design of steel and iron components started in 1870. The piers and abutments were completed in 1872, but became a source of ridicule as those piers stood waiting to receive their undesigned superstructure. The construction of the superstructure started in 1873 after 28 months of research and development. The bridge company was seemingly always in danger of running out of cash. Stocks, bonds, second, and even third mortgages were all in play, organized by the famous investor Junius Morgan. To keep the project on track, Morgan and Eads put both bonuses and penalties on the line. Morgan stipulated that the arch construction needed to be complete by December of 1873, with an entire substantially complete project by March of 1874. The arches were installed by December in only 9 months, and the roadway deck was completed by 1874. The bridge was tested with an elephant crossing the bridge, and superstition is said that an elephant would not walk on an unstable structure. Eads, never shy about a good show, also had 14 fully loaded steam engines line up on the bridge's lower deck. The New York Times called the St. Louis Bridge the 8th wonder of the world. The grand opening of the bridge was on July 4th of 1874, a massive celebration with William Tecumseh Sherman cutting the ribbon, and Eads himself, of course, the guest of honor. At the outset, the bridge was not a headline success. The railroads refused to use the bridge because they already had a profitable agreement with the ferry services for transferring freight across the river. The Panic of 1873 hit while the work was being finished, and it was 8 years before the bridge turned any form of a profit after Junius Morgan gained ownership of the bridge in a messy bankruptcy. Even engineers ridiculed the bridge. At the 1874 American Society of Civil Engineers Conference in Chicago, the St. Louis Bridge was called unorthodox, a dangerous deviation from the tried and true methods of the industry. Eads was an outsider, but sometimes that's what an industry needs to push it forward. It's interesting to note Eads Bridge's performance among its contemporary and more conventional bridges at the time that engineers liked. Bridges that were constructed much faster and much cheaper as pin-connected trusses or wooden trusses. The 1877 bridge constructed at Omaha was destroyed by a tornado in 1882. An 1856 Rock Island Bridge burned down within a year. Rock Island Bridge No. 2 was destroyed by a tornado in 1866. A bridge upstream in Hannibal collapsed in 1872 after being struck by a barge. And another bridge at St. Charles failed after a train derailment. Eads Bridge has withstood pier hits, cyclones, and derailments. What can we take away from Eads Bridge? What is it that makes Eads Bridge built to last? James Buchanan Eads, without a doubt, pushed civil engineering forward. with his innovative vision for something more than the most cost-effective bridge. Eads Bridge required caisson construction pushed to the limit and the application of the lightest and strongest arch material ever, steel. To vet out the steel, Eads and his engineers invented modern material testing and along the way developing the modulus of elasticity. Was this bridge costly and overdesigned? There's no doubt about the cost, but it's hard to say that it was overdesigned when you think about the fact that the bridge survives 151 years later. Eads himself said, "This bridge will endure as long as it is useful to man." Eads Bridge has endured. Eads Bridge outlasted every other bridge on the Mississippi River, becoming the oldest bridge crossing the Mississippi. Eads Bridge is most certainly still useful to man, and Captain James Buchanan Eads Bridge is in fact built to last.